Good morning. The topic of my presentation is comparative study on existing tall buildings with structural irregularities and its effects on cost and performance. There will be two case studies that will be presented. The first case studies will be the effect of building configuration and irregularities on the cost and performance of your structure. And the second study will be the influence of eccentricity on the building cost. So as a background, the structure could be considered irregular if it contains a regular distribution of mass, stiffness, strength, or due to geometrical configuration. Structural irregularity directly affects seismic performance during strong earthquakes. And failure of structural elements are mainly concentrated at these locations of irregularities. So there are two major types of irregularities. You have the horizontal and the vertical irregularities. For the horizontal irregularities, you have stiffness irregularity. For the horizontal irregularity, you have the torsional irregularity wherein the maximum deformation, the ratio of the maximum deformation with the average deformation is greater than 1.2. Next would be the ray entrant corners. That is, the building offset is greater than 15% of the building dimension. Third will be the diaphragm eccentricity, non-parallel, load factor resistance system, and out-of-plane offsets. Next will be the stiffness irregularity, wherein the stiffness of your columns is less than 70% of the average stiffness of 3 floors above. The mass irregularity refers to the mass that is greater than 150% of your adjacent floor. Next, you have the geometric irregularity, in-plane irregularity, and capacity discontinuity, or known as a weak story. So, the main intent of this check is to identify the locations of stress concentration and to design the critical members for these additional loadings. So, building amplification is required to the structures which does not conform with the code limits. The first of these checks are accidental torsion. The code stipulates that you have to design for at least 5% mass eccentricity for both directions. Sorry. Okay. Ikaw na lang. Okay. Okay. 5% eccentricity for direction. But if the ratio of the maximum deformation to the average is greater than 1.2, we need to amplify this eccentricity. The next requirement will be the 25% backup frame check. The special moment frame is required to resist at least 25% of the seismic forces. So if you cannot attain this requirement, we need to amplify the frame forces by a specific scale factor. Next, please. Okay, for our first case study will be the performance and cost analysis of existing building projects, considering the building irregularities. Next. So there are 8 buildings in review: Sequoia, Portico, Solinea, Solstice, Chroma, Verb, High Park, and Ariza. The highest, or the tallest of which, is Sequoia with 56 floors, and the shortest will be Ariza with 28 floors. Next, please. So the typical floor area is shown for each structure. Sequoia, it is a post-tension slab system with outrigger columns and a central core wall. Portico, Solinea, and Solstice are dual system with conventional frame of slabs and girders. Next, please. Next is Chroma. It is a combination of flat slab and perimeter beams. Verb and Abriza are conventional system with both slabs and girders. But for High Park, even though that has a conventional system, but there's a lateral force resisting discontinuity along the weak axis due to the absence of connecting girders. Next, please. Okay, for our first building in review, Sequoia. So Sequoia is a 160-meter tall building with 56 stories. So the typical floor height is 2.9 meters, and the structural system was designed based on the low, middle, and high zone. So the ideal mode of response of the structure should be translation for the first two modes, which is the X and Y axis, and the third mode will be rotation. Next, please. Okay, so the building performance was checked for both interstory drift and building displacement. So this is within the code limits. For building amplification factor for torsional, it does none. But since the structure was designed using performance-based method, the 25% backup frame requirement by the code was not needed. Next, please. Next will be the portico tower. Portico is a 128-meter tall structure with 42 floors. So the first two modes are translation, and the third mode will be rotation. Next, please. So the building performance within the code limit, and again, none of the amplification factors are applied. Next. Next is Solinea Tower. It is a 96-meter structure and 32 floors. So the mode of response is translation for both of the first two modes, and translation and the rotation for the third mode. Next, please. The building performance is within the code specified limit, but in this case, there's amplification for 25% backup frame at 9th and 12th floor, and the maximum amplification factor is 2.46. Next, please. For Solstice, it is a 142-meter tall structure with 48 floors. So the mode of response for the first two modes are translation, and the third mode will be translation plus rotation. Next, please. The building performance is within the code specified limit, but you have a penalty for 25% backup frame at the second to the fourth floor. Next. Next is Chroma. Chroma is a 146-meter tall structure with 48 stories. So the mode of response is translation in y-axis for the first mode, and also the translation for x at the second mode. The third will be rotation. Next, please. So in this case, only the penalties for the third to 10th floor for the 25% backup frame. Next. Next, you have the Verb. The Verb is 132-meter tall structure with 42 stories. The mode of response is translation for the first mode, the second mode is rotation, and the third will be translation plus rotation. The building performance for interstory drift and building displacement are within the code specified limits. In this case, the backup frame is penalized only at the third floor. Next, please. Next is you have the high port. The mode of response is translation for the first mode, rotation the second mode, and third mode will be translation plus rotation. Next, please. The building performance is within code specified limit, but on this structure, it is the only structure that we applied for the torsional amplification factor. So it is on the second to 8th floor, and it has only a 1 floor for backup frame penalty. Next, please. And lastly, you have the last structure, the Abrisa structure. It has translation for the first two mode and rotation the third mode. So the interstory drift is within the code specified limit, and there's no amplification factor. Okay, next, please. So the results were compiled and tabulated, and each building parameters are scrutinized to identify what factors contributes to or affects the cost of your structure. Next, please. So it is being shown that based from these values, next please, that high part tower has the highest rebar ratio and also the most amplification factors. Next, please. If you're going to graph those values, so next, please. It shows a trend of a direct relationship between the number of amplification factors with regards to the rebar ratio. So high part tower is almost a regular structure with both irregularities for both horizontal and vertical was penalized by the code to be the highest rebar ratio. Next, please. And also, we take note that the post tension slab and flat slab has a higher rebar ratio with the conventional slab, with the exception of high port. This is maybe due to the minimal contribution of slabs for participation of your seismic resistance. Next, please. Okay. For our second case study will be the effect of eccentricity on structural cost. So the eccentricity that I'm referring to is the eccentric distance between the center of mass and the center of rigidity or center of stiffness. So a Vibe tower is a 48-story structure. We made a study of 4 schemes. The first scheme is that the shear wall, which is in red, are located at the opposite end of the core wall with a middle column which is colored in blue. For scheme 2, we just remove the middle columns and maintain the configuration. For scheme 3, we relocate the shear wall adjacent to your core wall. And then scheme 4, we remove the middle columns. Next, please. So it shows that as we relocate the columns that is adjacent to your core wall, there will be a shift of, or the large stiffness was shifted, and thus creating a large eccentricity. Okay, for this case, the large eccentricity caused the outer vertical members to be subjected to additional stresses due to torsion. So in this case, scheme 2, which has the lowest eccentric distance, has the lowest Lieber ratio, and then scheme 3, which is in red, has the largest eccentric distance, has the largest Lieber ratio. Next, please. And also we take note that as we move the columns, the structure becomes more flexible and becomes more economical. This is due to the fact that the fundamental period has increased and thus reduced the code base shear. And then next, please. Okay, for the findings that structural irregularity are directly related to cost. The more the structure is more irregular is your structure, the more will be the large concentration stresses and will be expensive to construct. Flexible structure within the code prescribed limits is ideal for economical design. Minimize eccentric distance by balancing your vertical element to minimize the eccentric distance between the center of mass and center of rigidity to reduce the structural cost. And also, to eliminate the 25% backup frame as part of your coding requirement, we will use a performance-based design. Okay, thank you.